Moment about a particular axis. Now, so here's a tire iron. You put a force on it that here's the distance from the lug nut to your hand. You put this force on it, you're going to get a moment in this direction, but it's only the moment in this direction that you care about. So it's the perpendicular distance from the line of action of the force to the line of action of the axis of interest that you take, if the force is perpendicular to the y-axis. In this case, it is. So it's only d sub y. Force times d sub y will give you the moment parallel to the lug nut, to the axis of the lug nut, and cause the lug nut to turn. That's why, you want this to be kind of short, actually, so you get the maximum effect of the force. Actually, you want this to be long and this to be short. Because anybody who's changed a tire knows the tire iron can fall off pretty easily. Formally, you have an axis of interest where something can rotate, axis of projection. You get the moment of some lever arm and force. Now you want, well, this is just the total moment dotted into U sub A. The magnitude of M sub A is this moment dotted into U sub A, which is, there we go, it's right here. That's the magnitude. The dot product gives you a scalar. That's the magnitude. The stuff in the square brackets is the magnitude. U sub A is the vector direction. M sub A, the vector direction of M sub A is going to be just the unit vector along the axis. So there's your vector formalism. You can set it up in Excel. You can set it up in MATLAB, by the way. Sometimes Excel is just a little more convenient, a little easier to see. So sometimes I'll use Excel, sometimes I'll use MATLAB. Sometimes I'll use New Octave, which is a free open source replacement for MATLAB. So let's look at this example. We have determine MAB produced by force F right there, which tends to rotate around the AB axis. So UAB is, that's the first thing your book calculates, UAB. 4/10 in the x, 2/10 in the y, divided by the root of the sum of the squares. And we want the moment about this axis, but first of all, we'll need to calculate just the moment about get the moment about point A, and then we can get the moment about the axis. First of all, we'll get that. So first step, getting this. And I'll flip to my Excel spreadsheet in just a second. So here's the radius vector, here's the force, and we want this directed along UAB. So let's go, we'll come back to this. I'll go to my Excel spreadsheet for right now. Okay, let's take a look at this. RC, the distance from the origin to the force, 0.60.3 meters. F, negative 300 newtons in the z-hat direction. So the spreadsheet calculates 180 newtons, the y direction. The R from A to B is this, 0.4.20. Magnitude this. Unit vector this. And the magnitude of the unit vector is 1. And the angles are all given here. Okay, unit vector. M dot AB. There we go. And let's expand this. row just a minute here. There we go. So you can see what I wrote. There, I think that's enough. Some product. Here's M right there. Here's row 6. In this case, we're taking the unit vector, m dot that unit vector, UAB, this magnitude. And then you take this magnitude times that unit vector to finally get this. And sanity check, the magnitude of MAB should be equal to m dot UAB, which it does. Sanity check. Sanity check. The unit vector of MAB should be the unit vector of RAB. Sanity check, yes. Okay, back to here. Just remember, 7236 is our moment Newton meters. You'll notice that UAB is the same thing the Excel spreadsheet calculated. The Excel spreadsheet is doing these calculations, is what it's doing. And the Excel spreadsheet is running these calculations also. 80.5, that's exactly what we got for the magnitude. And then 7236 is what we got for the vector MAB. Okay, couples. This system has no net force. It will only cause an object to turn. So if we can separate things into forces plus moments, that can be really good, because if you get the force acting on the center of mass for an object, for example, that tells us it's translational motion. And the moment about that center of mass will tell us it's rotational motion. Important for dynamics, not just statics. Zero net force. The couple moment is just going to be the distance between them crossed into F. So you can take the moment about this and get R cross F. R cross F, just like this. RA plus R is equal to RB. So you'll notice when you add the moments, RA cross F plus RA cross negative F, excuse me, plus RA plus R times positive F. Well, the RA's cross F cancel out, and you get R cross F. You wind up with R cross F at the end. Same moment about any point. Key idea here. Okay, so let's go through this. And the couple moments, it's pretty easy. 300 times 5, and we can look at clockwise and counterclockwise. So that's clockwise. There it is, negative 300 times 5. 200 times 4, 200 times 4, 800 clockwise, another negative, and then 450 times 3, the two 450s times the 3 distance, that will give us 1350, and that's positive, for a total of 1350 minus 800, that's minus 30, that's 550 minus 6 minus 1500, or negative 950 clockwise. Pretty easy problem. It's kind of nice that way. That's the nice thing about couples. We'll go on to the next problem, pick up couple some more in just a second.